Now, we are a small audience, but we are very powerful in the end of the day, so let's give a really warm round of applause for Conor. Thank you, Conor. The stage is all yours. And please, guys, ask questions on Slido, all right?
Thank you for the introduction, and thank you for attending what I believe is the last talk of this conference. How's everybody enjoyed the conference so far? All right. Glad to hear that. Hopefully we can end on a high note. I think, questions we'll save for the end because we've got the Slido thing. If you do have a very urgent confusion that you'd like clarification on, just feel free to shoot your hand up. I can repeat it so folks on YouTube, I don't mind getting questions in the middle. Welcome to my talk entitled The Power of Function Composition. This is going to be a talk that is very code heavy for, I think, CraftConf. I think I saw a couple talks. Jessica Kerr, she had some code. If you were Justin Sanders' talk, he had some code. You're probably going to see the most code out of any talk that you've seen so far at this conference, I think. I didn't see all the talks, but I prefer to lean towards code-heavy talks, and hopefully you're going to see some programming language that you've never encountered before. My name is Conor Hoekstra. This is an About Me slide. I'm not going to spend much time on this, but I just want to provide a little bit of context of sort of my background. I've been in industry for 10 years now. For the entire duration of my career, I've primarily been a C++ developer. At one point, even for 2 years, I contributed and worked on the C++ ISO committee, working on language and library evolution. And in the last 2 to 3 years, I've actually become more of a Python expert. I probably write Python as my day-to-day driving language. But at the bottom here, you can see all these esoteric languages. Some you might have heard of, like Haskell. That was my favorite language at one point back in 2018. But in the since 2019, the tail end of it, my favorite languages, probably my top 5 favorite languages, are all these array languages. You probably heard of APL. You probably haven't heard of BQN, Uiua, J, and Jello. But if you have, you're going to enjoy this talk. And if you haven't, hopefully you're still going to enjoy it, and you'll have your mind blown by what these languages are capable of. Also, as mentioned by Ricardo, I have 4 different podcasts. Probably the most interesting one is the one on the far left. This has been going on for a few years now. It's a weekly podcast. We're getting close to 200 episodes. We primarily focus on C++, but the last 5 episodes have been about Swift. Before that, we've talked about Rust. And the 2 middle ones are about array languages. So if you're interested, if you like podcasts, feel free to check those out. You can find links to all of my podcasts. I also have a YouTube channel, getting close to 100,000 subscribers there. Links to all of this stuff can be found at content, as well as a PDF slide deck of these slides if you want to refer back to this at a later point in time. So let's get to the talk. Function composition. You probably have heard of this, but the main point that I'm going to drive home, or hope to drive home in this talk, is that there are many different flavors. I call these function composition strategies. Most of you probably only know of function composition through operators and functions, the first 2. But what I'm going to demonstrate is that there are other strategies for composing functions. In array languages, these are typically show up in the form of trains as well as operators. And in a very esoteric language called Jelly, it shows up in the form of chains. And then in the stack languages, we're going to focus on Uiua. You don't really get composition, but it's superficially the same thing. And it's a very interesting language to look at. So 5 different function composition strategies. We're going to go through 8 different languages. We're going to start off in Python because hopefully we're going to start off on a foot that everybody can understand, and then we're going to get into stuff that probably is going to be a bit more confusing. Usually I save kind of the summary, the goal of the talk, to the end. I'm going to show it here right up front. So this is probably overwhelming, but this is basically highlighting the point of this talk. You've got 5 different function composition strategies. Everything in white that isn't about to be highlighted is an operator. So there's kind of a color coding at the bottom. White equals operator. Blue is for functions. This is in Haskell. So Haskell has both functions and operators in terms of their function composition strategies. Then we've got trains. This is green. So you can see that APL, CAP, J, and BQN all have trains in their languages. Then in Jelly, we have chains. I haven't encountered chains in any other language other than Jelly. And then Uiua, which was just released in September of 2023. So depending if you're watching this on YouTube, that might have been a couple years ago. But as of today, it was just over half a year ago, closing in on a year. And last but not least, that's the stacks that come with Uiua. Uiua is an array language combined with a stack language. And I'll address, if you're not familiar with these languages, what the differences are in a couple minutes. But this is what we're going to work towards kind of understanding. Not every single symbol, but more that we have these different strategies in these different languages for achieving function composition. So up in the top left-hand corner, I have this FOF. If you want, you can guess what it stands for, but I made the term up, so odds are no one's going to guess it. Any guesses in the audience? I heard that might have been right. Function of functions. You are 67% right, 2 out of 3. It's not function of functions, although it could be. It's a function-only function. And everything below it is basically a combinator, but a subset of combinators, at least as I consider them, are function-only functions. So let's start off there. What is a function-only function? Well, that's a combinator. So we have to answer that question first. What is a combinator? So this is the academic definition of what a combinator is. I don't really like it. It's a lambda expression containing no free variables. I technically am a bit of an academic, but I don't even really know what this means. Like, I do know what it means, but it doesn't mean anything to, the larger audience. So I prefer the definition is this one, a function that deals only in its arguments. So that means that if it refers to some global, or even if it refers to a constant inside of it, that means it's not a combinator. So anything like a reduction or a scan or a map that might take an argument, a function as an argument, or data as an argument, but doesn't refer to any global state and no constants. So say you had a function that was like a Forex currency exchange, but it has a hard-coded constant in it. That's not a combinator. So it only deals in what you pass it. So when I first saw this, or understood this, I thought, that kind of sounds like a pure function. Are they the same thing? And if you don't know what a pure function is, here's my definition. Same input equals same output. There's like several definitions out there, no side effects. You might have heard of referential transparency. But the idea is no matter what input you give it, you're always going to get the same output for that given input. So are they the same? And the answer is not really. You could think of a pure function that refers to a hard-coded constant that always gives you the same answer, but because it refers to that constant, it's not a combinator. So there is kind of like they're almost the same, but there are these corner cases. On top of this, there's something called a higher order function, which is the yellow circle. If you haven't heard of a higher order function, it's a function that either takes as an argument another function, or it returns you a function. So are these the same? Not really. You can think of higher order functions, once again, that are not combinators because they refer to constants. And a higher order function could take a function argument that refers or does something that making it not pure. So all of these are very, very closely related, but technically you can find corner cases where you just have a combinator, but it's not a higher order function and it's not a pure function, vice versa. So I like to think, this is not my mental model. This is technically the definitions. In my mental model, if we pretend we're in Haskell land, where the Haskell land is only pure functions, and technically you can have not pure functions in Haskell. We'll ignore that corner of Haskell. Imagine we're in a pure functional land where every function is a pure function. We can then change the diagram to look like this. And I prefer this as my mental model. So the question is, what is a combinator? Is the combinator that I'm referring to this green circle? And the answer is almost. There's actually a subcircle, though, that is the following. These are combinators that are always higher order functions and combinators. And I refer to these as like combinatory logic combinators. There's something called the SKI combinator calculus that defines all these combinators, SKI, etc. They fit in this blue bubble. Technically, though, K and I are not necessarily higher order functions. K and I can deal in data. They don't necessarily take as an argument a function. So therefore, we got to kind of put K and I off to the side. They're outside the higher order function bubble. And then we have this. So this brings us to the function-only functions. That's this pink circle. So a function-only function is a higher order function and a combinator that deals only in functions. Every single argument is a function, and the thing that it returns is also a function. And I searched all the literature, read many papers. They don't have a word for this. Many of the combinators in the SKI combinator calculus, basically all of them, are function-only functions. Their arguments are functions, and what they return is a function. But there's no way to refer to this, so I've come up with FOF. We've added it to HOF, pure function, and combinator. And note that if you've heard about combinators in other contexts, like parser combinators, that's a different type of combinator. I mean, it's still a combinator. They are functions that they deal only in their arguments. But it's slightly different than the combinators that are in combinatory logic. So like, this is a very confusing thing that when I was learning all this stuff, I was like, why this article kind of refers to something else? This is my mental model, and hopefully it will help you for the rest of the talk. So in summary, oh yeah, and this animation is to show that technically there should be no yellow and blue only intersection. Everything should be pink in that like overlap, because there's no such thing as a function only function that's not like a higher order function inside the combinatory logic combinator circle. That's a FOF. Like, that should be filled, but I didn't have the energy to customize a shape. We stuck with circles. And if Kevin Henny was here, he'd probably give me, question. We're going to get to that. And so the question was, what do K and I stand for? You're like 3 slides ahead of me, but we're going to get to that. So this is just a summary of everything I just explained. A combinator deals only in its arguments. Combinatory logic combinator, it's from combinatory logic. Function only function, it consumes and produces functions only, as opposed to the higher order function at the bottom that consumes or produces, and a pure function, same input, same output. So let's get to combinators. What are these things? I've spent 10, 15 minutes, talking about this hierarchy, this Venn diagram. What are combinators? We're going to start with the elementary combinators. So these were defined in a 1958 textbook by Haskell Curry and Robert Faze. Haskell Curry did his dissertation on combinatory logic and is basically the father of the field. He spent 3 decades writing papers. And in this textbook, he defined the 5 elementary combinators. The I is the elementary identificator. C, permuter. W, duplicator, B, compositor, and K, cancellator. You'll start to understand these names. They kind of seem very, highfalutin, if you will, but I like them. And we're going to start by going through these one by one. So the question earlier, what is I? I is a very simple function. In fact, the first time I saw I was like, what? That's a thing? Like, this is useless. It does absolutely nothing. Why would you ever want a function that just returns what you passed into it? But it becomes important when you start to compose things together. We're actually going to use it in the Clojure example coming up in a few minutes. So you pass it something, just returns it to you. K, this is the elementary cancellator. You give it 2 arguments, and it returns you the first one. So basically, it cancels the second one. It throws it out. This becomes very, very important when you start to compose functions, and we're going to see that when we get to the example. Next one, W. W is known as the duplicator. This is the first function-only function. Technically, K and I, if you pass I 42, it'll return you 42. So that's why it's not necessarily a higher order function. You can pass it data. W, you have to pass a function. So F is a binary function that you pass 2 arguments to. But when you apply W to F, it turns that into a unary function that basically you pass the same argument twice. So if plus is your binary function, it takes 2 arguments, and you apply the W combinator to it, you get a function that you could call double. Because if you pass 10 to it plus, you're going to 10 plus 10 is called doubling. Also, you might be thinking, what's the point of that? Very, very, very useful. Many times, you have a function where you're passing the same argument twice, and being able to convert that into a unary function is very useful. So, a little digression here is that I'm referring to binary functions and unary functions, and I might slip up and refer to monadic and dyadic functions. So I tweeted this up at one point, and I realized that there are basically 2 sets of words to refer to the arity or adicity of a function. And both of those 2 words, arity and adicity, just mean the number of arguments your function takes. So the first time I actually heard binary operation in C++, because it's defined in a lot of the standard algorithms, it says binary operation. I was always hearing this in conference talks and thinking, why are they talking about bit arithmetic and like, ones and zeros? This has nothing to do with that. And that's because binary operation there just meant an operation that takes 2 arguments. So on one side, we've got the, I believe it's the Latin ones, unary, binary, ternary, quaternary, and then the Greek ones for adicity, niladic, monadic, dyadic, triadic, and tetradic. You're probably only going to hear binary and unary for the most part, but whenever you hear those words, it just means a 1-argument function and a 2-argument function, just for clarity. So that's the end of that digression. Let's keep moving on. We had the W, F is a binary function, and it returns you a unary function. The next combinator is B. This is probably the most common combinator across all of the languages. Most of the times when you hear people talk about function composition, or you hear compose in mathematics, this is what they're talking about. You've got two unary functions, f and g, and you're just applying f after g. But a part of the point of this talk is that this is just one flavor of many different flavors of function composition. And last but not least of the elementary, or second last but not least of the elementary combinators, C is similar to W in that it takes a binary function, but what it does here is it flips. It swaps the order of the arguments. And if you know anything about Haskell, this is called flipping Haskell. And I think probably every other functional language, I don't know what Scala calls it, but they probably all have something like this. And last but not least is S. So this is where things start to get a little bit confusing. S takes a binary function f and a unary function g. It applies the unary function g to its right argument, and then along with the initial argument, x, as its left argument to f, you then pass those two things. So this is where it starts to get a little more confusing. Is like, where would this be useful? This also exists in Haskell as the applicator. You can spell it AP, or you can spell it as an operator, which we'll see a bit later. So these are the elementary combinators, but we've got a ton of these. On top of the elementary ones, we've got things like D, B1, Psi, Phi. And this isn't even an exhaustive list. What you can see is that basically all of the stuff after IK and KI, these are all just function-only functions that are just basically manipulating the way that you're applying things. So in a language that doesn't have support for combinators, the way that you achieve this stuff is just by parentheses. You're just wrapping some operation so that it happens first. But that can become cumbersome and very inelegant, which is why I love combinators so much. So for the rest of the talk, we are going to be working our way through one example in 8 programming languages. And this example is called Special Array. It's actually from a LeetCode contest that happened 2 or 3 weeks ago. Once again, if you're watching this on YouTube, it was probably a number of months ago, if not years ago. And this is a very, very simple problem. But I love it because when you solve it in Python and then solve it in these other languages, it highlights the elegance of function composition in these combinators. So what is the problem? You're given an array, and it's considered special if every pair of adjacent elements have different parity. Parity is a fancy word for is it even or odd. So what you want in order to have a special array is you want an even number, odd number, or odd number, even number. You never want to have 2 adjacent elements that are both odd or both even. Pretty simple. And if we think about how we could visualize solving this, we've got an array of 4 numbers. We can see here that it's even, odd, odd, even. So this would not be special. How would we solve this? First things, we want to look at 2 adjacent elements at a time. Then we want to check, are they odd or are they even? So we'll say 0 means even, 1 means odd. And then we just want to check, are these equal to each other? So really what we want is, are they not equal to each other? So the first and the last box are both not equal. Middle one is equal, obviously. And so we're going to end up with basically true, false, true for our adjacent elements. And then we just perform a reduction on this to see, are all of these ones? If there's a single 0, we end up returning false, which in this case is 0. So hopefully that made sense. We're going to walk through the Python example first, but these are the 8 languages we're going to cover. So very quickly, I think everyone is probably familiar with Python, #1 or #2 language in the world, dynamic imperative scripting language, although probably Python devs are offended if you say scripting. But that's what I mostly use it for. Haskell is a static, strong, pure functional language. Clojure, also a functional language, but it's dynamic and it's a Lisp. It's probably one of the most modern Lisps. And then at the bottom, these are all array languages. So APL was created in the 1960s, and it is a dynamic language that has infix and prefix functions. Cap is basically just a different flavor of APL, but it was created in 2020, and it has a couple different features that we're going to look at. BQN is an APL-inspired language, but it looks slightly differently. J is basically an ASCII version of APL that was created in the 90s. Uiua was created in September 2023, just like over half a year ago, and it's the one that is a stack language combined with an array language. And then Jelly, Jelly's just crazy. I'll explain Jelly when we get to it. But it actually was designed to be a code golf language. The goal is to have the code as short as possible. That is the entire point of the language. The fact that there are interesting language design in this language is like an accident. when I was just, and I'm saying jelly, but here it's showing the Jello logo. Jelly is so confusing that I had to build a tool to basically translate the jelly in order so that I could understand what was happening. And this is coming from a guy whose favorite languages are all Unicode symbols, and I can like speak all of these languages. And I got to jelly, and I was like, all right, I have no idea what's happening here. But we'll get to that later. So we're going to go through all of these one by one. First up is Python. So Python only has function composition via functions. I think technically with the meta language or the meta programming, you could set up some operators. But in the way that Python is idiomatically used, you only have function composition via functions. So this is our first solution. Is array special? We've got for I in range, the length of our array -1, because we're going to have to check side-by-side elements. And then for each element, we're basically going to do a modulus 2 to get whether it's even or odd. And we're going to check, are they equal to each other? And as soon as they are, you return false. If you get to the end, that means you haven't seen any that are adjacent and have the same parity, and therefore you return true. I don't like this code at all, but it's where we're going to start. Does anybody have, I'm not sure if there's any Python devs in the audience, what's the first thing you might do if you were refactoring this? Just one small change that makes it much nicer. Enumerate? Enumerate is a stepping stone to what I was hoping for, which is basically iterable unpacking. And if you use a zip, you can do that. So we can avoid our index by zipping our initial sequence nums with what's called the tail of that sequence. So we drop the first element, and then zip will short circuit, and then we can destructure or unpack our two adjacent elements into x and y. And now we don't have to do that nums bracket I plus 1. This is better. I still don't love it, but it is better. The next adjustment is that now that we don't have indices, we can turn this into a generator expression. So we have the all reduction that we're checking. And note that we had to switch our sign. Originally, our binary operation was equals, and we were returning false. But now, because we're checking, I guess we could have done this with none and kept the binary operation. But I like all better. So we're saying all of these are not equal to each other after you perform the modulus 2. Question? Yes. So nums. So the question was, doesn't bracket 1 colon n bracket give you a list? And the answer is yes. So in our example where we have a list of 4 numbers, nums bracket 1 colon n bracket will give you a list of 3 numbers. And what zip does is it basically combines that list of 4 with that list of 3, and then it takes 2 elements at a time, x and y, out of it. And if they don't have the same length, it'll short circuit. So depending on your language, zip actually might have a different behavior. I think in Haskell they have like a zip and then zip with longest, and then they have like some null value that they'll put in. But yes, great question. So here I like this a lot better. It's a lot more declarative. We've only got basically a single return statement, whereas in the previous solution we had 2 return statements. I don't love that. And we've got a generator expression, which in general is more efficient than a for loop. So this is great. However, this is where function composition and combinators comes in. When I see x modulus 2 does not equal y modulus 2, I think that's a combinator. Probably the rest of you do not. But I dream in combinators, basically. We've got a single unary operation, which is basically checking whether something's odd, and we're applying it to 2 different values. So we have a binary operation, the not equals 2, that's applied after applying the same unary operation to 2 different values. So this pattern is first 1 unary operation to 2 different values, and then you take the result of those 2 unary operations applied and pass those values to a binary operation, in this case not equal. That combinator is called the psi combinator. And if we use the psi combinator from a library called dovekey, we get the following. So psi takes 2 arguments. The first argument is the binary function, ne, which comes from the operator module. I actually, I think ne is a little bit, it's a little bit short. I would like neq a little better. But also I'm an array programmer, so every time they shave off a character or something, it makes me happy. And then the second argument is the unary operation. So basically, odd is going to get applied once to x, once to y. That produces 2 values, and then those get passed along to the binary operation not equal. And what's really nice about this is we don't need to actually pass the x and y in to this function psi that we've just created. We can make use of map, because map is variadic in Python. And we can just call the 2 range overload of map and end up with the following. Right, and so this is psi. explicitly. F is our binary function, G is our unary function, and then we're passing, this is technically incorrect, there should be a Y there, there's a small bug on this screen. So it should be G of X, G of Y, and then we're returning the results of that to F. So if we come back here, as I mentioned, we can simplify this code to just use the variadic map and get rid of our zip. And this, compared to the initial code, I actually like a lot better. It does require you knowing what the psi combinator is. And arguably, psi is not a great name because it means absolutely nothing other than some person in the 30s, named this combinator, this function pattern, psi. But it is, thought provocative. Can we give this a better name? And I really like this piece of code. So that's the Python code, which we're actually going to come back to a couple times. Let's move on to Haskell. So Haskell has both function composition in the form of functions and operators. So this is our solution in Haskell. We've got map odd, which is just going to turn our list of integers into trues and falses. And then we've got this horrendous zip width not equal angle star angle tail. We'll come back to that. And then we've got basically the equivalent of our all reduction in Python. So what is this zip width not equal angle star angle tail? This is actually the semantic or moral equivalent of what we had in Python when we had our variadic map. Zip width is just our variadic map. It takes 2 ranges. Technically, this one takes 2 ranges. If you want one that takes 3 or 4, they have to hard code them. But zip width takes 2 ranges and applies a binary operation element-wise to each one. So when we had our map with our operation and then nums and nums 1:, that basically the map is the equivalent of zip width. And this angle star angle, that's the S combinator. Remember that function where we had a binary function and a unary function? You apply the unary function to the right argument and then pass that along with the initial argument to the binary function. Tail is another way of spelling that bracket 1:, end bracket in Python. It just means drop the first element and take the rest of the list. And similar to the zip in Python, zip width is a short-circuiting function. So once again, if you have your initial list of 4 elements, you tail it, then you get your second list, then you take those 2 lists and pass it to this zip width not equal. And then you end up with a list of trues and falses, and then you just do your all reduction. So even though this is, I think, pretty overwhelming to look at, it's semantically the same thing, or morally the same thing as the Python code. So this, as I mentioned, you can see that the S combinator is right here in the middle. You can also spell this with AP. And I didn't really mention this, but we also have the B combinator silently right here. So in Python, you don't have that. You basically just pass a function that you've applied as an argument to the next function. So you get this kind of inside out. You got to read the inner thing first. In Haskell, we just spell this unary function composition with a dot. So we have the B combinator twice and the S combinator. Pretty nice, but we can do better. And how is that? That's by knowing your algorithms. So one of my theories is that it's the combination of algorithms and combinators that really leads to beautiful code. There is this pattern, zip width, binary operation, S combinator, other operation with the tail, is just map adjacent. So map adjacent is similar to map, but it embodies that tail trick. So when you're zipping with your tail, that's what map adjacent just does out of the box. So instead of spelling the S combinator and then having to explicitly write out tail, map adjacent just folds that stuff into what it does. So all you have to pass it is a binary operation, not equal to. And on top of this, fold one and, there's a nicer way to spell that, but a lot of people forget about it because it's and that's a terrible name for this function in my opinion because it means almost something else in every other language. But and is the equivalent of all in Python. But we're not done, because what do we have on the last 2 lines? We're mapping odd, a unary function, and then we're mapping adjacent, a binary function. We can combine those using the psi combinator, once again, into a single operation. So on in Haskell is what they call the psi combinator. So now we've seen the B combinator, the S combinator, and the psi combinator. But we've now simplified our code to just 2 operations. We started off with tail, map, zip width, fold one, and all we're down to is and map adjacent with a little bit of combinator magic. So really, really cool. All right. We're going to go back to the Python solution very quickly. Imagine what this code would look like if we had a map adjacent. So let's slide this code down. And this is a potential implementation of adjacent map. And we're using something called pairwise. This is basically the same thing as our zip tail trick, But the difference is that you can do this lazily because it comes from a library called, I guess I didn't include it. It's called itertools. And then, once we have a JSON map, we can just substitute this in. Still the same length, but now that we have this adjacent map function, we can make a further simplification. If you don't want to use a psi combinator, now you can just pass map of odds as the first argument. So now because we have a more expressive algorithm, we're able to avoid using the psi combinator, because basically inside of map adjacent is the psi combinator, which is really, really nice. And we're actually going to come back to this Python code after we look at the jelly code at the very end. So anyways, the point being is that it's not just combinators. It's combinators and algorithms. The more algorithms, the richer set of algorithms you have, the less you need to lean on these combinators, which I think a lot of people find confusing. So next up is Clojure. We're going to burn through Clojure. They have both functions and operators. I just wanted to show another functional language. So this is a Lisp, and this arrow operator, it's known as the arrow operator, the threading thread, what is it called? The thread last macro, and also the thrush operator. It basically says, whatever I pass to you first, thread that to each operation as the last thing each time. So first you pass it to partition. That's going to basically take adjacent elements two at a time. Then you're going to perform a reduction, because each of those two elements is going to be in a list. And then that's going to return you trues and falses of whether they are equal to each other or not. And then at the end, you're going to do another reduction called, is every single one of these things true? And because every is expecting a predicate function, a function that returns a true or false, but we already have a list of trues and falses, this is where we use the I combinator. So identity in Clojure is the name of the I combinator. An alternative way to spell this, if you don't want to make use of the map, is the following. This is just destructuring your two-element list into A and B. I'm not sure which one I like more, but I just wanted to highlight this so that we had a couple different functional languages to look at. All right, so this brings us to probably the most exciting part of the talk, our array languages. So we've got APL, BQN, J, and CAP. Technically, I could put a yellow circle on functions because you can name combinators and spell them out yourself. But what comes with the language are operators and trains. And so we've already seen operators. They're basically just infix operations. But what's a train? A train is basically the juxtaposition, the putting side by side of two or three functions. And those correspond to a combinator. So in J, the toTrain, putting two functions next to each other, corresponds to the S and the D. And then putting three functions next to each other corresponds to the phi and the phi1. And then every other language, it's B and B1 for the toTrain and the same for the three-train, except for CAP leaves out the three-train, which is very, very interesting. Probably from this table it doesn't look like it, but it leads to language implications. So if we go back to our combinator list in Python, if we hide the ones that we didn't just see, this is S, B, B1, D, and phi. And if we get rid of S and D, because those are only for J, this is basically the two trains are the first two, and the three trains are the second two. So B, just unary function composition. We've seen that before. B1 is basically a sibling of B, where first you apply a binary function to two arguments, and then you apply a unary function after that. Super, super useful. And then phi and phi1, these ones are a little bit more confusing, but they're very important to the array languages. G is a binary function for phi, and then it's going to come with two unary functions. And then it's going to apply each unary function to the same argument, and then take the results of those two operations and pass them to a binary function. And phi1 is basically the same thing, except instead of applying them to two different arguments, or the same argument, you're applying it to both arguments twice. We're not going to see phi1, so you can kind of ignore that, but we'll get into phi a little bit more. So I think this brings us to the live coding portion. We're going to see how this goes. I'm going to take a quick sip of water while I switch to. And so you can, that is carbonated. We did not want that. So you can go and try this online. This is tryapl.org. All of the 5 languages we're going to look at, you can do this. This is all inside the browser. So hopefully the internet doesn't cut out. Otherwise, this is going to epically fail. So this is APL. And basically, that's a list, 4, 3, space separated. So the first thing we want to do is we want to check if this is odd. So this is 2 modulus. And that gives us back a list of zeros and ones. So 1 means it's odd, 0 means it's even. So pretty simple. 2 characters, and we're already like halfway through our problem. The next thing we want to do is we want to look at 2 elements adjacent to each other at a time. So there's something in APL called an n-wise reduction, and the n here is 2. So what this means is that we're going to the comma is a catenate, so it's going to say, give me two elements at a time and catenate them together. So when you do this, you get basically the first 0 and 1, then you slide over 1, then you get the next two ones, then you slide over 1, and then you get the next 1, 0. But we don't want to catenate these. We want to check if these are not equal to each other. So we replace this comma with a not equal to's. And then when we do that, we're going to get back 1 for the first one, 1 for the last one, but a 0 in the middle, because those two are equal to each other. And then once we're done this, we only got one thing to do, and that's to do an and reduction, or our all in Python. And we're done. Thank you, thank you. But here's one of the upsetting things about dialog APL, is that this is not tacit code. So tacit code means code that doesn't mention its arguments. So when we're writing it without the parentheses around it, it's just evaluating what it sees. It's kind of eager. It does the to modulus, then it does the n-wise reduction, and then it does the all. But if we put parentheses again, around it, that's forming a function. And unfortunately, this isn't going to work because of the 2-train, 3-train model in dialog APL. So what we need to do here is we need to put the identity, the I combinator, and then this is going to form a 3-train, which corresponds to the phi combinator. And then that's going to form a unary function, which, along with our n-wise reduction, will form another phi combinator. And then we have our and at the end. So it's a little bit unfortunate that the changing from like no parentheses to parentheses changes the meaning of the code. And it makes APL already, on top of the Unicode symbols, a difficult language to learn. But if I put the parentheses with the identity around it, it now works. So that's language 1 of 4. Let's now switch to cap. So cap is the alternative APL. And it's got some small differences, but for the most part, it's the same. However, it doesn't have the 3-train, or the fork. It only has 2 trains, which is really, really nice in this example. So we're going to do the same thing. 2 modulus. Thank God the internet worked. I was worried about that one. Then we're going to do our n-wise reduction once again. So we can show that we'll do the catenate first, and then we replace our catenate with a not equals 2. And then at this point, we're going to do our and reduction. So it's the same thing we just saw. However, because we don't have 3 trains in cap, this doesn't change the meaning of this expression, which makes it a much, much easier to learn. This is going to form a unary function because of something called left-bound functions. This is going to form a unary function because of something called left-bound functions. And this is already a unary function. And when you have 3 unary functions in a row, because of the lack of a 3-train in cap, it's just the B combinator and the B combinator. 2 B combinators, that's the simplest combinator. We evaluate this, and we get the same result. So this makes cap, when I discovered cap didn't have a 3-train, I was like, oh, I love the trains. Like, why would you get rid of the 3-train? But then I realized it leads to being able to compose these kinds of functions that are much, much easier to reason about. And when you put the parentheses, most of the times it doesn't change the thing that the function evaluates to. All right, so that is cap. We're going to go back to our other browser, and we're now going to go to BQN. So BQN, actually BQN stands for, it was supposed to be APL plus 1 for each of the characters. So A becomes B, P becomes Q. But then they messed up the L. L should have become M, but they added 2 to it. And so now the joke is BQN is APL plus Fibonacci. But yes, let's keep going here. So we're going to do the same thing. We've got 2 modulus. And you can see here that BQN pad, this site, it's really, really nice because you can evaluate multiple expressions at the same time. So we've got one that passes and one that fails. However, we don't have an n-wise reduction in BQN. So we have to do something else, which is basically a Windows function. So this is going to create a matrix 2 at a time out of our one-dimensional vector. And so because now we have a matrix, when we do our not equals reduction, we have to do that over the rows, which is a little bit more verbose to spell. So that's going to be not equals, if I can spell this correctly. And then we have to do this over our rows. So this is the equivalent of what we had as our n-wise reduction. However, because we don't have the n-wise reduction, we are now in the state where we have a 3-train, or we have a 3-train followed by a function, which is going to form the B combinator, and we can't have 2 B combinators in a row. So when we try to do our Python all, or our and reduction, which is going to be this followed by this, and note that all of the operators or modifiers in BQN are superscript. So it's the first language that I know of that disambiguates between two different types of functions as like regular characters and superscript, which is kind of cool. But you note that this is not the correct answer. And that's because we have two unary functions next to each other, and it's not parsing correctly. So in order to make this work, we have to put something that's called nothing, a little bit poorly named. If I can do this right. What is nothing? There we go. It's shift semicolon. So this now it parses correctly because we had to basically split our two unary functions, so it formed the B combinator correctly. All right, last but not least, actually we're staying here and we're going to J. So J is the ASCII version, so no more Unicode symbols. Same thing we do here, 2 modulus. We get back our zeros and ones. Then we have our n-wise reduction, which I believe if I do this correctly, this will give us ASCII versions of our enclosed lists. But now we can replace this enclose with our not equals to, which I believe is squiggly :/ for our reduction. And this should give us our 101. And then we've got our and reduction. The and is a asterisk period, and then the reduction once again is /. So better in the sense that there's no Unicode symbols, but I think worse from a readability perspective because they form their functions by basically using ASCII digraphs. And in order to make this work correctly, you basically and I got to speed up here. You basically have to put an identity here, separate this. This is going to form 2, 3 trains. And then once again, we need to do the same trick in BQN as putting a nothing. They call it cap here. And then this evaluates to 0. So that is all of our array languages. Let's keep moving along. This was in case cap failed. It succeeded. So our second last language is Jelly, which has chains. So I'll go through this quickly. We start off with 416. And Jello has keywords that then converts the keywords into the Unicode symbols in the Jelly language. So the yellow is jelly. And the green keyword is Jello, my interpreter, my way of translating. So first we have odd. That gives us our zeros and ones back. Then we have differ. This is a way of spelling our n-wise reduction where our binary operation is not equal to. And then after this, we just do all. And so the yellow expression, B over dot, D accent caron, and then A underdot, that is the actual Jelly programming language, 3 characters. Like I told you, it was designed to be a programming language for code golfing. But what's really interesting about this is that in Jello and Jelly, they use chains. Basically, they look at the arity of each function next to each other. And then they have basically just a pattern matching table of whenever you see 2 ones, that's the B combinator. And then that forms a unary function. And now you've got 2 ones next to each other again. That's the B combinator. So really, really interesting. I don't have time to talk about it more. But a couple other things to note about Jello is that here you note at the top, I replaced differ with a not equal to prior. Prior is just another word for map adjacent. And then the all with an and fold. But built into my little tool, anytime there's an opportunity where you can use a more expressive algorithm, I have something called the algorithm advisor that basically converts that into the thing and says, hey, you should use all here instead of and fold, or you should use differ here instead of not equal to prior. All right, last but not least is Uiua. We're going to do this super quickly, and that is going to be back in our Chrome browser. So Uiua is a stack and array language. So all the functions in a stack language are prefix. And really interestingly, if I can type correctly, is that you go modulus 2, and you type the prefix of the function that you want, and then when you hit Control Run, it turns that into the corresponding symbol. So you don't actually need to remember how to type all the keyboard shortcuts. So that's modulus 2. Once again, we have to do Windows 2 to get our matrix. Then we have to do a rows, reduce, and then we want, I think it is not equal to, you spell it with the exclamation equals. Once again, you hit Control Enter. It turns it into all the symbols. And then last but not least, we have our reduce, and it's going to be the minimum value. So if we type min, that gives us our answer. So interesting language. Note that there's actually no combinators here. Because it's a stack language, you get the essence of unary function composition, but it's just evaluating the thing that's at the top of the stack. So very, very similar. It still has the rank polymorphism inside of the other array languages, and it combines that with a stack. So I think this is like spiritually or morally equivalent to what the array languages are doing, but it's a much, much simpler model. And this language has gotten pretty popular compared to the other languages, not compared to Python. Anyways, that's the last language. So these are all of the solutions in the array languages. And I think there's a lot of interesting things happening in here. I don't have a ton of time to dive into it, but you can see that at the bottom is the spelling of it in English. And that's what I see when I read the other code. So my dream is like a readable array language that you can read odd, different, all. And this is much nicer when compared to the Python code. So this is a summary of all the different types of function composition across the languages. In conclusion, what's the point of all this stuff? Sure, I love this stuff. It's fun to look at. I think it leads to extremely beautiful and elegant code. But that's a subjective statement. You might look at this and think, I'm going to stick with Python. I'm going to stick with JavaScript. Or maybe not JavaScript, but you'll stick with whatever language you're working in because that's what you think is beautiful. I think this stuff is beautiful. But the point is that you've got combinators here. And these combinators combined with algorithms lead you to much simpler code. If we go back, so this is Algorithms, Data Structures plus Programs. It's a book that was written by Nicholas Wirth, and it's what we named my first podcast after. I am starting to think that in array languages, you only have one data structure. It's the array. So it's not really algorithms plus data structures. It's algorithms plus combinators. And then that equals beautiful code. And if we go back to the Python solution, this is with the adjacent map. But what if we use the differ that we had in Jelly? It simplifies to this. Now there's no combinators. But my knowledge of this stuff comes from studying combinators. And so my goal is write code that doesn't have combinators, but you need expressive algorithms, and combinators are a route to discovering those algorithms. So I encourage you, go check these languages out. You can find them at all of these links. If you go to the GitHub repo, I have everything there. And check out combinatorylogic.com if you want to learn more. And thank you. Oh. Also, I got a couple libraries. I think we're way over time, so come find me afterwards if you want to ask questions. I'll be
Conor,
around.
Thank you so much. Actually, what I do with all the speakers is, first of all, this is from us to you.
Thank you.
We really don't have more time for questions. We have only 3 questions. So here's the thing. I'm going to ask the 3 questions after I give the announcement. The announcement is go to the main stage if you don't have interest in the next 3 questions. OK, we have the final ceremony there. Just go, relax, watch the final keynote. And we have 3 quick questions. If you can be very brief, we can do the questions, all right?
I'll do 10-second answers, or you can find me out afterwards.
Yes. So the first one is, working mostly in semantic domain models, which functional language would you choose to be explicit in domain terminology in code?
Find me afterwards so you can explain that in more detail. Yeah.
All right. What's a monad?
Go watch the recording of Sanders' talk. He explained it.
All right. That's really, I love it. Most companies require careful dependency analysis already. Why should we give up our options?
Also find me afterwards. I don't have a 10-second answer for that.
All right, guys. Thank you very much. Thanks for coming to the craft, being a